Has this ever happened to you? You want to wear a cool hat, but all you have is some dumb code. Well, you're not alone. In fact, tens of people suffer from this issue every single year. Luckily, I'm here to help. Today, I'll be talking about Steve, the system I built for converting code into a hat. But first, what do code and hats even have in common? Well, hats of course have a physical structure, whereas code has an abstract structure known as the abstract syntax tree. Today I'll be talking about the exact process that you need to go through to convert an AST into a physical structure that you can wear, much like a hat. So, let me introduce Steve, the system I built to turn my code into a hat. Steve is short for Syntax Tree Parser and Builder, which is just a really natural acronym that conveys that Steve is a system that takes a piece of code, extracts its syntax tree, and turns it into a physical geometry. And here are the basic tools. Of course, Rhino 6 for Windows and the Grasshopper environment that goes along with it, and the Pufferfish extension for Grasshopper, and then Python 3 as my main development environment. How does Steve work? There's just a couple main phases. First, it all starts with a tasty homemade piece of code. I use Python, and so this is one of the sample scripts that I started out with. Then we have to pass it into Steve, who will steal its skeleton, which is the abstract syntax tree, process the skeleton, and finally create a physical geometry of that skeleton. It's all Steve. So let me talk a little bit about abstract syntax trees. I've used that phrase a couple times already, but I just want to be perfectly clear exactly what I'm talking about, because I'll be talking about them a lot for the rest of this project. Essentially, there are a lot of different programming languages, and they all look pretty different, but what they have in common is that they all have a syntax, which is a well-defined set of symbols and the rules that define their behavior. So the abstract syntax tree represents the syntactic structure of the program. So if we start out with a very simple program, this is just a Python script of 2 lines, the abstract syntax tree might look something like this. We've got a set of nodes connected with edges, and since it's a tree, not just a regular graph, it does not have any cycles, so there will never be any loops in the tree. Each node represents an operation, a variable, or some other value with syntactic meaning in the code, and the edges represent the direct relationships between them in the program. So in this simple example, the module just represents the high-level module, the program itself, and then we have one node that represents the declaration and assignment of the variable I, and another node that represents some call to the print function that takes arguments. One thing to note is, even though in the code we can see that print takes the variable I as an argument, we don't see an edge between those two nodes in the AST, and the reason for that is because the AST represents the structure of the code, not the structure of how the program is executed. So we know that during runtime, this variable I has a direct relationship with this function call, but syntactically, there isn't a direct relationship between these two nodes. Abstract syntax trees are called abstract because they don't contain every detail about the code's behavior, but they do have practical applications. They're often used in compilers and program analysis. One of their main functions is just determining whether a piece of code is a valid program in the target language. That's how you detect syntax errors. And you can also see them in more theoretical contexts, like defining type systems and stuff like that. Alright, so I've introduced all of the high-level steps that Steve needs to do. Let's get started talking about the details. Before I jump into everything, this was a really code-heavy project, so I will be talking in a good amount of detail about the code that I wrote. but I won't explain every single line. So I'll put all of the code that I use into a GitHub. So the first step, like I said before, is to get the AST. This step is done completely outside of Rhino and Grasshopper. Getting the AST itself is fairly straightforward to do, since it is a structure that has practical applications when running code. There are already a lot of tools out there that exist to extract the AST from a given piece of code. So for this project, the only extra step we have to do here is to make sure that we get the AST in a clean format that we can store in a text file to easily parse later. Okay, so I plan to use Python for the entire project just to be compatible with all the code we need to write in Grasshopper later. So I wanted to write a simple script that would take a Python file and print its AST. My first attempt was just to use the AST library that's built into Python. This is the original script that I wrote to do that. It just uses the system and AST libraries to take in a file name as an argument and parse the AST and dump out its entire contents. And this definitely works. We can see that we can pass in a Python program and we get all of this output. This is the entire AST with every single detail. So, of course, if we were a compiler or an interpreter, we would want all of this information. For the purposes of this project, I decided that I only wanted to preserve two things about the AST. I wanted to preserve its structure, because of course that's going to become our physical shape, and I also wanted to preserve the general type of each node in the tree. So for example, this node is an expression node, and there's a call, a name, just the general types of each thing in the AST. And my idea was that in the tree, each node of a specific type would have a different shape. So the final geometry would still have information about the program encoded into it, even if it's not necessarily human readable. It's still technically all there. So when I saw this, I was like, oh god, I'm gonna have to do a lot of parsing and a lot of cleanup with this output to get what I need. But then I remembered it's Python and there are helpers for everything. So I found the AST dump helper on pypy.org. And basically it worked exactly as I wanted it to do. If I just use the defaults, I don't even pass in any extra flags or anything. I can get the AST structure and the general type of each node with none of this extra information or annotation. We can see it's much cleaner, and the hierarchy of the tree is enforced with this white space in the output. So this is essentially all we need to do for this first part. Just write our script, pass it into the AST dump helper, and dump the output into a text file. And that's it. This text file is now going to become our input for the real action. One thing to note, remember earlier I mentioned that abstract syntax trees are used to determine whether a program is syntactically correct. This means that you can only get an AST if your program is valid. So I have a program here with a syntax error. You can see I've mixed my tabs and my spaces as Python hates, which I think is insane. But if I try to run the helper with this piece of code, I'll just get an error. And that's because this piece of code cannot even be parsed as a program. So this is good because it means that all of our resulting geometries that Steve is going to generate are all geometries of syntactically valid programs. Okay, so that brings us to step 2, which is processing the AST. This step is actually done within the Grasshopper environment, but I wrote and tested the code in my regular Ubuntu terminal before actually plugging it into Grasshopper, so that's where I'm going to demo it. At this point, we have a text file that contains the structure and the node types of the AST. And we need to traverse this text file and create a data structure that stores those types in the same hierarchy. This step might first seem redundant because we just went from an AST, which is a tree, to a text file, and now we need to go from that text file to a different tree structure. You know, why not just traverse the AST directly and not have that text file as an intermediary? There's a couple reasons for that. First, I didn't want to have a strict dependency on a specific language or tool used to extract the AST. For the purposes of this project, I'm just working purely in Python, so the AST dump helper will suit all of my needs, but in the future I might want to try getting ASTs from programs written in different languages. So like a C++ program would require a different tool to get the AST. So I don't want to couple it too directly to Python itself or specific helpers. So in that case, it's just easier to use text files as a generic interface. And I also wasn't entirely sure if the AST library and helpers would be supported in the Grasshopper environment. They are sort of part of the standard library. But my other concern about just using the AST library in Grasshopper is the fact that Grasshopper is a data flow environment. So it's going to rerun all of its operations when any of the inputs are modified. And I was a little worried about triggering the entire system if I made a small change to like a complicated program file. I first had to come up with a structure that would be easy to traverse. As far as I know, Python doesn't have an n-ary tree structure in its standard library, where you can have some node with some undefined number of children. One probably exists somewhere out there, but I don't actually use Python nearly enough to be aware of it. So my solution was to store the tree as a dictionary. Each node in the tree was represented as a dictionary with a single key, which is the type of each node, and the value that it's mapped to is a list of its children, which are also nodes represented as dictionaries with a single key. And we can see all of our leaf nodes are dictionaries mapped to an empty list, so they're nodes with no children. So the process of parsing is essentially doing a depth-first construction of the tree from the text file. So as a quick review, depth-first traversal is a way of recursively visiting every node in a tree by essentially following a branch as far as you can until you hit a leaf, and then working back upwards. So here we would go all the way down to this first leaf, notice that this node has no children, go up to its parent, see if that parent has any more children that can be traversed back down to a leaf. If not, keep working back upwards till you hit a node that does have unvisited children, and visit those nodes, and repeat. The twist here is that when we're constructing the tree, obviously we're trying to traverse it in a depth-first manner, but the tree doesn't actually exist as we're doing it. It starts out very similar to the depth-first traversal that we just saw. This is a very simplified version of an AST text file we might encounter. We start out by placing the first node, which is the root. We go to the first line, we see it's more indented than the previous line, so it must be a child. We add it as a child. And again, the next line is also a child of the previous line. Now, when we hit this next line, it's not more indented than the previous line. So we know that it's not a child of the previous node. But, unlike in depth-first traversal, since this tree doesn't completely exist yet, we don't yet know which node is the parent expression node. So what we have to do is essentially iterate backwards through the current branch until we find the node that is less indented than the current line, and that's how we can find the parent of this new node we're trying to insert. For this child, it's pretty simple. We just have to look up one node up in the branch, and we find its parent. And now this becomes our current node. So when we go down to the next line, we see, oh, this line is less indented than the previous line. And so we need to look for the parent. First, is the previous node the parent? Of course it isn't. Then we have to look at that parent, or that node's parent. And this line still isn't more indented than it. So we continue to traverse upwards, root in this case, and we find that it is the child of the root. So these two nodes are siblings. This is the code I wrote to essentially do that exact algorithm we just walked through. Here's the recursive function. It tracks whatever was the current most recently visited node and its associated list of children as its subtree. This is our easy check where we can immediately tell that it just has to be added as a child of the previous node. This is a slightly harder case where we need to locate the parent of the current node. And I just literally looped backwards. I've got some structures for mapping because we can't physically loop backwards through the dictionaries. There's no pointers or anything going on. So I just have some lists maintaining the relationships between the nodes that have been examined so far. There might have been a more clever way of doing it. When I wrote this, I literally had like 1 brain cell per hour of sleep, which was 4. But it works, and we can just call this function, and it will return us the tree represented as a dictionary. So if we run it, it's using the Hello World Python script that I've used before as an example. We see that we get this wonderful looking dictionary, and if we format it so that the children are printed in the appropriate order, we see that it retains that structure that was given to us in the text file, but now it's a data structure that can be easily traversed. It's finally time to make the geometry. It's time to really start plugging things into Grasshopper. Everything up to this point has just been sort of classic, data structures, algorithms. It's all a little annoying to write, but pretty well-defined stuff. Now it's time to connect all of that to some physical shapes. We're going to do some math, and we're going to make those physical representations of the ASTs. My goal was to create a system in Grasshopper that takes an AST text file and some set of polygons as input, traverses the file, does the parsing, and then traverses that final data structure to create the physical shape that looks like an AST. This step is more like 2 steps. So the first step is I just did some experiments with moving around the input shapes, creating the edges, and converting them to physical geometry. And then the second step was actually writing the operations to create and place the physical objects corresponding to each node in that data structure that we've just built. For the experiments with the geometry, first I just checked that I could take in some set of polygons and locate all of the centers of them. Then I experimented with the Grasshopper API to be able to create a copy of a given input curve and move it to be placed at a certain distance from the center of the parent and draw a line connecting the 2 centers. Finally, I pass the set of lines into an offset box, which just creates a slight offset from the original line, so you have 2 lines that are in parallel. Then I pass those offset lines and the original set of polygons into a boundary box to make them all into surfaces, and then an extrusion box to make them 3-dimensional. Once the physical part was done, I just needed to do the final step of converting the parsed AST structure to a set of curves and lines that could then be made into its physical geometry. This is going to require another classic tree traversal algorithm, the breadth-first search traversal. So just as a quick recap of breadth-first traversal, unlike depth-first, where you try to follow a branch all the way to the end, you traverse the tree in horizontal layers. And you can do this recursively, or I prefer to do it iteratively using a queue, where you just trace the next layer of unvisited nodes. We start out with the root, add the 2 children to the queue, and then visit the nodes in the order of the queue. As we visit each node, just add its children to the queue until every node is visited. But of course, just like with our depth-first traversal, our breadth first traversal also has a twist. For us, we're not just traversing the tree, we're also generating the geometry and maintaining the physical structure as we traverse the tree. So, for each level that we traverse, we place the physical shapes of the nodes for the children when we add them to the queue. We start out by just placing where the root is going to be located, and then we begin our breadth first traversal. When we add the children to the queue of nodes that need to be visited, we place their physical geometries. So by the time we visit those nodes, they have a shape already located in physical space, and we can do the same for their children. Finally, when we reach the leaves, they don't have any children, and we're done. We've completed our geometric structure. There's a little bit more detail that needs to go into this, so I'm going to show you the code. Here we are in Rhino, here's our Grasshopper file. All of this stuff down here is just the experiments I had talked about before with creating the copies of the input curves and placing them in space. Everything else, all of this, that's all Steve. It's the system that's actually going to create the physical geometry of the AST. So first, let's take a look at all of the inputs. We've got our text file, which contains our formatted AST text file from the AST dump helper. We've got a list of input curves. That's what these polygons are. These input curves are going to be used as the different shapes we use for nodes of different types in the tree. We've got these two sliders, drop distance and max fan-out angle, which are used to calculate the placement of the children. I'll talk about that in a little bit. Down here, we've got our big output block for all of the debugging print statements. So let's take a look at the Python script. This is where all of the logic happens, the brain of Steve. This is all of the stuff we talked about earlier with just building the tree from the input file. And this is the breadth first traversal section. It does exactly what I just showed earlier, creates the geometries as we traverse through each layer of the tree. Couple things to note. I mentioned that I wanted to make sure that the final geometries retained some of the type information of the AST. So the way that I do that is I maintain a map between each type that's encountered in the AST and one of these input shapes. So if we encounter a type that has not yet been mapped during our traversal, we randomly select one of these shapes to represent a node of that type. So that means every node of the same type will have the same shape, but since there's a pretty limited number of input shapes, and obviously many possible node types, and the selection is random, it does mean that not necessarily every node of the same shape is of the same type. Down here is where the physical placement occurs. I talked about these two sliders earlier, drop distance and max fan-out angle. Drop distance defines the Y distance, or the vertical distance below a parent that a child will be placed. And max fan-out angle basically defines the spread over which the edges to the children should span. So the way that we place the children in physical space is we divide up that fan-out angle into a set of center angles that define the angle that the edge should have to the child from the parent. And then we just do a little trigonometry, a quick tangent, using that center angle and our Y distance, the drop distance, to determine the X offset that the child center should have from the parent center. And then finally, we add a line connecting the parent center to the child center. And the result of all of that, we get a list of curves, which is a list of all of the polygons representing all of the nodes placed in physical space. We've got a list of lines, which are the edges of the tree connecting the parents to their children. And we've got a list of points. I was mainly just using that as debugging. And then finally, all of the set of edges is passed into that offset box that I talked about earlier in my physical geometry tests, and that creates those two offset lines, which are then passed into this boundary box along with the curves representing the nodes to create a set of surfaces. So at this point we've got a flat tree in 2 dimensions, and then it's extruded so we get height. So if we bake the result of this extrusion box, we have a 3-dimensional representation of the abstract syntax tree. Now we can run it. We've got our Hello World abstract syntax tree text file as an input here. I'm going to enable this input, and we can see here's our abstract syntax tree. So if we take a look at this in perspective, we can see this is a physical shape that represents our abstract syntax tree, which is pretty cool. A couple of things. A lot of my inputs are sliders. This is sort of a parametric design. You can get different looking structures from the same syntax tree. They'll all have the same general hierarchy, but for example, I could change the drop distance, which will alter the distance from which the distance from the parent that the children are placed at. I can alter the maximum fan-out angle, which will decrease that horizontal spread of the children. And note that every time I change one of these inputs, the entire tree is regenerated, so all of the types change, so they don't necessarily have the same shape every time. And that's because these curves are being randomly selected to map to the node types. I can also mess with the offsets to determine how thick or fine the edges are between the nodes. And if I wanted to, I could also change this vector that defines how high it's extruded. I think I've got it set to about 1/2 inch or so. I also wanted to talk about this specific AST just a little bit. This is the syntax tree of that Hello World program that I've been using as an example throughout this video. And one thing that seems a little bit off about it is that there seems to be a cycle. And earlier I emphasized abstract syntax trees never have loops. Even if it's a program that has a loop, the syntax tree does not have a loop. But it looks like there is a loop. The reason for this is there actually is not a loop. These are actually 2 separate children, and just because of how I'm dividing that angle spread, they always just happen to overlap exactly. The centers are always placed at the same point, and in some cases, even though they are nodes of different types, they're also assigned the same shape. But what is kind of interesting is, even though this syntax tree will print and appear as though it has a loop in its final form, it still is kind of legible, because you can see this is the original code, and this is the syntax tree that was extracted from it. We can actually read this model. You can see the root is just the module. We've got 2 children, a function, and this is its list of arguments. We see it's an empty subtree, so a function that takes no arguments. And then it has an expression, which is a call to some sort of function. We've got the name and the load and the constant. So here, this triangle child that's being covered up by this pentagon is a constant representing the string Hello World. This is a crown. And meanwhile, over in this other branch, corresponding to this expression, this is the branch that represents the call to crown. So there's a bunch of, extra stuff that goes along with that function call. And the final node is this load, which is this pentagon that's covering up that triangle. And the final load is actually the load of what is going to be displayed. So it is the load of this constant, essentially. Syntactically, we don't know that they're the same, but since we know what the original code looks like, they kind of represent the same value in a way, even though they're nodes of different types. And in the syntax tree, they have no knowledge of each other. So it's kind of interesting. One more example that I just wanted to show was kind of the main reason that I wanted to build Steve in the first place. My thought process was that I'm building a system that can take in any Python script abstract syntax tree and make a physical geometry for it. The system itself is essentially one big Python script. So why not pass it its own syntax tree? Steve can print his own skeleton. It's like a self-portrait. Here's a text file with the entire syntax tree of Steve's brain. It's quite extensive. And there's a good bit of nesting in here as well. And overall, there are just a lot of nodes. If we go ahead and run this, it'll take a little bit, but here it is. This is the syntax tree of Steve. You can see it's completely illegible. There's no way of distinguishing any of these nodes. Even if I were to maximize the fan out and the drop distance, which I've done before, there's just way too many nodes. And the issue is that they all need to be placed in physical space. And due to the hierarchy of the AST, there's a very limited area in which all of the children can be placed where we can still connect it to the parent and make it look like a tree. So there's just always going to be overlap. It's very dense, particularly up here at the top, which is all of that, DFS and parsing and all of that stuff. It's also very skewed. That's because towards the end, we've got a lot of if-else statements, so a lot of branches and a lot of outcomes that only happen in specific branches. I actually have sliced this model, and it was way too big to print directly and way too complicated to print directly, so I cut it up into 4 pieces, and I printed some of those pieces. Let's just go see a printing montage and see the final results of what Steve can do. Hope you enjoyed my incredible original 3D printer remix. Okay, so finally Steve is complete, and I tested it out on quite a few different abstract syntax trees. So the very first model that I tried printing was these tiny little ASTs. These are actually snippets of a much larger AST, so these don't actually represent an entire program. I passed the program into the AST helper and then just clipped a subtree from the text file to test it out. But it worked out pretty well. You can see this is the root. The root's at the top, 2 branches, and they're both of the same length. Since they printed so small, they're not super legible. You can't really read what shapes each of these nodes are supposed to be. But I ended up making them into this necklace, which is kind of hard to see when it's not being worn, but it looks pretty good when it's being worn. The way that the ASTs sort of fit together made it look sort of like a computer-generated lace, which I thought was kind of cool. I also printed the AST of a single function from the very first research project I ever worked on. I did try printing the entire AST of the whole project. It was over 6,000 nodes, or almost 6,000 nodes, and Python just would not even parse it. I probably could have changed the recursion depth to handle it, but I figured if Python wouldn't even parse it, Rhino would definitely just crash if it had to generate that many nodes. So I just did a single function. The AST itself looks pretty good, but when I scaled it down to print, I made it way too thin. So the copies turned out really flimsy. Some of them didn't even come off the build plate, and the ones that did broke into a lot of pieces or just peeled up from the build plate during print and got pretty messed up. So this one didn't turn out too well in terms of the physical object, but that was more just through my own error, but the actual geometry of it turned out really well. And of course we've got the Steve self-portrait. So this is 3 parts of the AST. I divided it into 4 parts. And there were 2 parts that were much denser than the others, and then 2 sort of edge pieces that were a little sparser. So the reason I broke it up into 4 parts was because the original print time estimated by the slicer for the entire AST was like 4 days. So I split it up, thinking that it would, be faster to print it in parts. And the model that I showed you earlier was sort of this triangle form, and I thought maybe I could make something that was kind of like wing-shaped out of it. So I decided to print 2 copies of the AST. And when I duplicated it and cut or sliced all 4 parts of it, the entire print time turned out to be more than 4 days anyways. I haven't printed the 4th part yet. But this is the root part. This is the very root of Steve, all of the initial logic. And then this is one of the corner pieces, the edge of the tree. These printed pretty well. There was a little bit of build plate adhesion issues at the very beginning, and you can see there's some sort of rounded edges where it started peeling off the build plate during print. But for the most part, the printer was basically able to just handle that, and it would print over the top. So the final face of it is perfectly level. I ran into a lot of issues printing this 3rd piece though. This is another one of the edge pieces. I believe it's sort of a bottom part of the tree. Since it's much sparser than the other 2 parts, there were a lot of build plate adhesion issues on the initial layers. And since these edges are so thin, it was really hard to correct for them. So when the printer tried to go over it, the filament would just move around. So the underside of this is really messed up. And you can't see it on the final model, but a couple of nodes actually just broke off altogether or were never properly connected in the first place. So it was a little frustrating. This is actually from my 2nd attempt of trying to print just this specific piece. The first time it printed a few layers down and just started, like, there were just disconnected pieces. It just really wasn't adhering at all, so I tried to re-level the bed, recoat the bed in glue, and I got a slightly better result, but still not all that good. And the 4th piece that's remaining is one of the pieces that's supposed to take over a day to finish printing, so it's not going to be done by the time I finish editing this video, so I won't be able to make it into anything really cool until much later. And then finally, the part I've been advertising this entire video is the hat. The hat made out of code. It's actually a crown, because remember, in the Hello World program that I've been showing you, we had that little function that said, "Hello World, this is a crown." This is the AST of that very program. So it's the program that prints "this is a crown," and I made it into a crown. It's a little hard to see all of the details, but we've got 5 copies of the syntax tree. These are placed root side up. The center one is placed on its side, and then just symmetrical on the other side. And what I wanted to do was I wanted to sort of try combining the 3D printed forms with different materials. I have done some stuff with wire before, so I figured I would just combine it with different types of wire to create the final form. And I decorated it with like sort of leaves and stuff because it's made of trees and I'm hilarious. But yeah, this is the final crown. Fun fact, it actually took me almost as long to build the crown as it did to write all of Steve. It took maybe 3.5 days to write all of the code for Steve, and it took about 2.5 days to construct this crown. And another fun fact, I actually ran out of wire about halfway through building the crown, and I had to go out and buy wire with my own money to finish the crown. But luckily I had won a bet that day, so my gambling subsidized my my final project. But yeah, there you go. That's how you make your code into a hat. Or that's how I made my code into a hat.